One of the most important branches of physics is quantum mechanics, which explains how atoms and particles behave in space. The only problem is that we don't really understand how they behave in space. Luckily, we have a very important tool called the Schrodinger equation that allows us to predict how atoms and particles behave in space just a little bit better. And today, I will be breaking down that equation so that someone with even little or no background in physics can understand it. Let's go. Alright, so here we have the Schrodinger equation. Now, don't panic, I know it looks crazy, but we're going to get through this. So first, we need to define a couple things. The first is the wave function. The wave function is just an equation that gives us the probability that a certain particle will be at a certain place at a certain time. The next thing we'll be defining is a derivative. The derivative is just the rate of change with respect to a certain variable. In the Schrodinger equation, this is the rate of change of the probabilities as a particle moves through space or time. So now we should start breaking down the equation. The first term consists of a constant, which is simply just a number, and the second part consists of a derivative of the wave function with respect to x. So this just means how the wave function changes as a particle moves throughout space. This entire term represents the kinetic energy of a particle. The next term, v times the wave function, just represents the potential energy. That's all there is to it. The final term on the right-hand side of the equation consists of another constant with another derivative, except this derivative is the rate of change of the wave function with time instead of position. So there it is, the Schrodinger equation in its entirety, completely explained. Now we should be able to solve a very simple problem. But first, let's set up some constraints so it's a little bit easier. The first is that it's in a box and can only move left and right, and the second is that it is always moving. The reason why we want it to always be moving is so that we can ignore potential energy. And by ignoring potential energy, we can make the equation just a little bit simpler like this. Next, we should choose an equation for the wave function. I made it very simple by choosing cosine of the position plus the time, but it's likely to be a little more complicated than that. Next, we need to take the derivative of the wave function with respect to position, and all that means is how the wave function changes as the particle moves. Unfortunately, I can't get into the specifics of taking the derivative of cosine, so just trust me when I say the derivative of cosine is negative sine and the derivative of negative sine is negative cosine. Next, we have to take the derivative of the wave function with respect to time. Luckily, I chose a simple equation, so it's just negative sine. And that's it. Just replace each derivative with their corresponding equation, do a little manipulation, and you have solved the Schrodinger equation.